Hello, everyone. So I wanted to pick up from where we were and make sure that I wasn't quite done with the writing of it. I did correct it on the record, maybe after some people were already gone. But recall this picture of you having some data and you're looking at product moments where you're collecting pairs. I didn't quite finish writing this horrible looking equation, and nobody should ever write anything down like that without talking through it from the inside out. I didn't, I think, finish writing the summation sign, and I didn't finish writing the 1 over n. So amend your notes. Little r of an x and a y is a sum normalized, so an average of the products of the distances of the pairs x and y to their averages, normalized by their standard deviations. And I then started to get into the fact that, well, this is a sum version for a finite set of n data, which mentally we were already hoping will approximate the true population value, which I went back and forth on, but I called it rho. Rho is from a population is a normalized version of the covariance that characterizes two random values in their population. So we have two random variables. What characterizes them? Well, a joint PDF. That joint PDF has moments. One of those moments is the covariance. When we scale that, we end up with a value between -1 and 1, and that's a measure of the relation, the correlation, the correlation. It's a linear measure of correlation in the sense of if that point cloud is stretched out, correlation is strong, those values are high. Then I built up that graph with the sums at the bottom right, and so that is a sample correlation coefficient. It has actual data in it. And we hope, and maybe I will draw my last arrow on it, that sample correlation coefficient, as n goes to infinity, turns into the population correlation such that we may use the sample correlation coefficient as an estimate for the thing we really want to know, and that is what is the population value. Now, when I'm writing this, I think that makes sense. I think intuitively you all know that the arithmetic mean is a measure of the, or rather gets close to the expectation. And we know that the standard deviation, the variance defined as this is a sum. It's got to be close to the true standard deviation. At least you have either prior knowledge or an intuition about it, that that's sort of a decent measure. But that doesn't prove it. That doesn't show it. And even if we know that as we keep taking more and more data, this is going to get closer and closer, the rate at which this happens is important. And so this is one of the various things that we're going to study now. Before I do, I want to introduce a handful of things that I think I need to do now because I'll need them later. So here we go. As always, please, the best way to interrupt me is to just open your mic and shout something, because I can't watch all my windows at the same time. So if you have anything, don't be shy. I think what and then that's right. And then I showed you that graph, which was straight from Wikipedia, with correlation clouds showing you strong, not strong, completely non-correlated. And I told you that if data are independent, they are not correlated. But if the correlation coefficient is 0, that doesn't mean at all they are independent. Sometimes it does, sometimes it doesn't. And the bottom row on that figure had plenty of examples of related variables like circular motion plus some noise, or a sine wave, or some kind of a weird smiley face trend that shows that there's a correlative relation between variables. And yet, you know, by the measure of the correlation coefficient, this being only so good, well, that is 0. So from that, you cannot conclude something is independent. But if something's independent, you can conclude that the correlation will be 0, which is a one-line derivation if you write down the definition of the covariance and the separability of the probability density functions upon independence, and then the equation just cancels itself out to it being 0. So some notes, I don't know, what shall I call it? I'm going to call it some more things. How about that? In college, I had a math book that was, you know, whatever, analysis or something. And then I had another math book that says additional material. And then I had another book and it had the title more additional material, which I thought at the time was hilarious. I did point out when I introduced the expectation that once you write it down and you know how to integrate, and you know that integration is just a glorified form of summation, that's a linear operator that you carry these things through. That's, I don't want to spend that much time on it, and that's why I gave you the homework. The variance, you know, there's squares involved, right? So that's a quadratic operator. And something that I know you all do at some point or another is collect a variety of data points, and then you'll want to combine them linearly. And actually, that's what my title should have been. Linear combinations of random variables I'm working towards a complete description of things as far as I can. But I know you already want to know that if you have X, Y, Z variables and you make a W out of their sum, then you know that the expectation of their linear combination is just the linear combination of the expectations. That was contained in the expectation. Since that's linear, I would call that a done deal. And that's my shorthand for your homework will ask you about that. Given X and Y, I might just write it. Let's have a variable X and Y. Let's have a Z that is a constant A and a constant B. In other words, a linear combination. My expectation is going to be my brackets, my averaging angular brackets. So the expectation of Z is A times the expectation of A plus b times the expectation of y. Why? Because when you write it down, these things just go on the inside, and the expectation of a constant is just a constant. And if you have a sum inside the argument of an integral, you just, do it twice and add the result. Okay. Well, I want to talk about the variance. And I'll begin with something that you definitely want to do. And now, because I'm going to run out of letters, I won't write x and y and z, but I'll write xi for, I equals 1 to n. So here, I am not using big N as the number of samples you draw from a variable x. Here, I'm drawing this x a little bigger to make the point that these are n random variables. Okay, so just because I can't go x, y, z, u, v, w, perhaps t, a, b, c, I run out of letters. Now I've inadvertently reused a, b, c that were constants before. Anyway, so x3 would be a z, x2 would be a y. You might get used to this notation. So my constants now would be something that you definitely also would want to do, something like this. You might have 1 to n weights that you wish to associate with your variables. And I know you've probably all done it at some point, where I'm now going to say, okay, I'm going to define a new variable, and let me make that a weighted mean. Red w is a constant. Every x is a different variable. And so now my z is not any one number, but it's a new random variable whose properties I want to estimate. Okay, so switch of notation, right? Just get used to it. I need to reuse what little letters and numbers I have available. So we know about the expectation of that variable. It's just a weighted sum of the expectation of the ones that go in there. The question here now is, what is the variance of such a weighted summed variable? This is in preparation for us knowing more about it than just the expectation and the variance. We're going to look at their distribution in a second, but you already all want to do this. You've got some data and you combine it and you want to do things like weighted means and weighted sums of this and that. And so I wanted to just write it in a way that makes sense to you, that if you do this, well, then you got to square and you got to do this and you can do that. And so it ends up being this. It ends up being, I'm going to write it this way for a good reason, the weighted, it's a quadratic combination, right? And so I want to write wi and wj, and I want to write that that's going to contain the covariance of the ith and the jth variable pair. So this here is quite an important formula, but it's also hopefully fairly obvious. If you don't know how to get there, it pays to write it out to verify that indeed it does come out like that. And if I give you one example, which would be, z equals a x plus by, let's say the temperature of the rock times 2 plus the weight of the rock times 3, that's my rockiness index z. I take 100 data of the temperature, take 100 data of the weight, I apply the combination, and I want to characterize the distribution, so the expectation, the variance, and everything else I may need to know about it, of this new combination variable. Well, we know what happens to the expectation. It carries through, and you probably have seen it before. At least this is a formula that I know comes up in books. Right, so you end up squaring the a's in this manner. World's oldest form of error propagation, characterizing the expectation and the variance of a linear combination of random variables. Example of 2, where I use 2 letters, x and y. Example of many, where I use x sub I and x sub j for as many as I want. And, well, that is the first level of generality. All right, I'm going to do something that I wish I had learned earlier. And so you're so lucky you're learning it in lecture 3. I'm going to do sort of slightly even more generally. I want to say that as opposed to xi as n random variables, I'm introducing a notation of x underbar, which in my notes, when I write it down, which I'll give to you, it's like a fat x, a bold x. It's a vector, okay? Is a vector of n containing those n random variables. And I am going to say that the expectation of that vector is the 0 vector. To make my life easier, we are very quickly coming to the point that much of what we study are perturbations from something we know, perturbations of transient nature around something that is of no interest and just, moving along. And if things have means that are non-zero or expectations that are non-zero, we'll just soon take them out because there is no art in summing and dividing, and we get there very quickly. The earthquake that happened last night, if you look on the record, there's nothing, and then there's something. I'll show it to you later. So the variable of the Earth displacement to us is basically 0 until something happens. So a demeaned variable or a 0 mean variable is very often the common start. And so Now I'm on a linear combination, and I'm going to do my z like before, and I no longer have a sum of w's, but I'm just going to use my vector notation here. So this would be a boldface capital Z to illustrate that this is a new vector. And I'm going to construct it by multiplying my x vector with a matrix A composed of constants. Compared to this here, now I have this. So in the previous example, what was A? What were the elements of A? Here, I'm going to say I took two letters, X and Y, and I sum and I multiplied by number and I sum them together. Cool. Here, I take a whole bunch of them and I number them instead of saying X, Y, Z. I multiply them by a number, W sub I, so unique to each of them possibly, and then I sum it. So this is my second version of a sum random variable. Here's my third version, which is, the simpler example again, where I have like an X and a Y and two random numbers, so two constants. I use the word random poorly. That make a new variable Z. So here now I'm carrying on that I'm making a new notation, and I'm saying, okay, my Z is a linear combination of entries of X, and I call that linear combination A, and A is going to be a matrix filled with constants. And now I want you to comment on the fact that the Z where my longest finger is a special case.
I have a question.
Yes, please.
Why is A a matrix instead of being like another vector?
Why? Because I made it so. I made a new thing that is possible. It is an operation I can do on a vector, and that is to linearly transform it. If I linearly transform a vector, there is a matrix with it. You are asking a good question, which is coming to my other question. And so maybe if you want to chime in and say, well, okay, I'm claiming that this Z where my index finger is on my left hand is a special case of this big A1. And so you please comment, or either of you please comment on what sort of A, which is more general, must this set of little W's have been in my previous example?
In the previous example, A was just another vector.
I will give you a minute to reconsider what happens if you multiply using a dot product, a vector with a vector.
Oh, then that's a scalar.
And that turns into a scalar. And if the notation is unclear, I will review it because people use them differently. So one up your answer and tell me something about the nature of A if it needs to apply to the previous expression with the little w's. Anyone else?
Is a diagonal matrix with the W coefficients along the diagonal?
Okay, so previous example was a simpler version. Had A, the doubly underlined matrix, being equal to, well, I'll just draw it, I guess. W1, W2, Wi, Wn, 0, 0. Diagonal. Maybe this notation needs a little bit more explanation in that sense than that, what does it mean what I write on the left here? I write that the ith entry of the vector z is the result of taking the jth entry of vector x, multiplying by the ith entry of the matrix A, and then summing over the dummy disappearing variables of J. That is my definition and notation of the dot product, in this case between a matrix and a vector. And so if it were to have been a vector with a vector, I would have had only dummy indices, and I would have obtained a scalar. Here I turn a vector through a linear transformation with a matrix into another vector. And again, you think of X as, the temperature, the weight, the molecular number, the reflections at 400 nanometers, whatever data you have, and you have some sort of index, some sort of thing you want to combine them into, and you're wondering what happens to the properties of that new variable that is now called Z. Okay, while I'm at this, and I have come to a good moment.
Frederick,
Yeah.
is the diagonal matrix right? Because it's not, Z is not going to be a linear combination if A is diagonal.
What is wrong with me wanting to multiply my X vector with just about any A's that I want?
No, my point is because you compare it to the previous example.
Yes.
Then Zi is just going to be weight 1 times x1, and the B has no value. So if you compare it to the previous example, then this would be wrong.
Oh, you are right. You are right. You are definitely right. Sorry about that. And I stand corrected on the record in multiple ways here. This previous one turns it into a simple single scalar number. You were absolutely right with the vector. So that was an even simpler example. In this case, I'm going to a higher order example of a general linear transformation. Thank you. And I'm going to do this here, creative line, thank you. This thing with the matrix. So the matrix is the most general. I want to consider a diagonal matrix. If the matrix is diagonal, then I just have W1, X1, and W2, X2, and W3, X3. And if I want to further sum that, I have the example from before, okay? So how about I say it's not identical? And in that notation, I really would have had a vector, and I would have written it. I might as well elaborate, right? So I wrote the previous example as a Z, which was not underlined, which is the sum of I over the red WI's. And so now, if I want to write that as a dot product, I would write it as little w the vector dot my x variables, and my w is just a set of numbers. Wn, just like my x is just a set of numbers. Sorry, this is random variables. I'm going to stick with my colors here. W is a vector of constants. These are random variables. I'll add this to an EG. I'll say this is rather. And if you think of vectors as needing to be columns with multiple rows, as I'm also about to do in a second, then you might also see this in a notation where you say, well, that's W transpose times X. So the previous example on the previous page was this one here, z equals w dot x. A diagonal example has come up where I turn x, where I turn n variables in an vector x to n new variables that are z's. But when A is fully populated, of course, a row of A could be a W. And so you could have various ways of doing various weighted linear combinations in all the rows of your A. I hope that has made it clearer rather than more opaque. So now I want to go to a non-dot product way. And I want to briefly introduce, because it makes it easier, an outer product between two vectors.
Frederick, just quickly, so the diagonal matrix example will just give you a vector of the weighted random variables?
Yes. But of course, so if there are off-diagonal terms, right, then they would be weighted sums, and I conflated those in my initial rendition. Actually, how about I make a new page? Or maybe I'll start saying here, right? So now let's think about X as a column. In the previous, I was just count them. They're indices in a vector, you know. The dot means sum over adjacent indices, and thereby remove a dimension, and then there's no need to talk about anything like an up or down column or row. Here I'm making another switch. All these things occur. And I'm saying, all right, now I'm going to stick my x1, x2, and so on, my n random variables into a column vector. And now I define the transpose of x as a row vector. And then I want to introduce the notation where I multiply x transpose without a dot, so not a dot product. If I call this y, I'm just defining some notation here. Now I define a matrix y for which the ijth element of y are the product of the xi and the xj. Okay, I'm just throwing it out here. Let me back up a little bit. Some variable, the expectation carries through. Weighted sum, that's how you combine the variances. You'll need the covariance. Simpler example again, square the constant. Don't forget the covariance. More generally, I'm deciding I'm going to stick all my variables in an X vector. I'm deciding they're going to be zero mean. I will want to make a completely arbitrary linear combination by sticking in a matrix and multiplying it out. One row of that matrix might have been the previous example, which led to, you know, one of those, which is a vector product, which turns into one variable. Back to the simpler example. The diagonal example is like a whole list of weighted things. So these W's are not the same as these W's. I'm just giving you examples that are different, but I'm sort of using the same symbols. Now I've introduced a dot product, the standard matrix notation, index notation for it. And now I'm introducing the outer product, for which I'm sort of having this geometric notion of this being a row, of a column vector made of rows, and the transpose of that being a row vector made of columns. And I define the XX transpose product as that thing that doubles up on the rank of this thing, gives me two underlined bars, whose ijth element is just xi times xj. And I'll tell you why I'm doing it. So now I want to talk about the fact that the covariance matrix that in this new notation, I now might have a definition that says, okay, the covariance of this vector variable, right? X, Y, Z, U, V, W, X1, X2, X3, X4. And I'm telling you they have zero mean because I just made it so, and I say it's always easy to do that. And so now I want to introduce the notation and the concept, which makes it easier, that if I think of this as a column vector, and I think of this as a row vector, and then I use my averaging brackets, then I want you to mentally think about the fact that if I'm on a diagonal of this here, then I have the expectation of x3 squared, which is the variance for the zero mean variable. And if I have an off-diagonal element, I have the expectation of the product of the first and the sixth variable, which is the covariance between the first and the sixth. So do you see this? That if I have a zero mean set of variables, that here I'm making a matrix, which I'll call C double underline. And if I want to read in there myCijth element, I'm telling you is, I'll do one diagonal, and then, you know, various dots, because they're all full. And so now here, I might have the expectation of the product of xi and xj. That's an off-diagonal element. And on the diagonal, I'll have the expectation of, you know, L squared, an II, a JJ, basically something squared. If I go back to my definition of the covariance on page 7, back in that day, not here, well, it was there, right? You see how these terms already existed last lecture, right? The covariance between x and y, now this is an xi and an xj, is defined as this, is the expectation of the product of these things distance to their own expectation. I've now set the expectation of either of them to be 0, and so it is just averaging brackets of an x and a y as an element in this covariance matrix. So the off diagonals are having all the covariances, and all the diagonals are the proper variances. But of course, you now see that these notions get a much more multidimensional nature. So some people in the literature call this a variance covariance matrix. It is the unfortunate thing that since statistics is everywhere sort of hacks it together with their own terms and notations. And then the real statisticians take over and you don't recognize a thing. And here I'm already illustrating that by throwing 3 different notations on the same page. But I'm doing this here because then I can generalize my prior error propagation in the following way. Now, if I define a linear transform with that big full anything goes A dot X, and I ask myself the question I wanted to ask, which is, what is the covariance of this Z? Right? So the notation helps us define a generalized, or rather multi-variable covariance. That's why I made the notation, bothered with the outer product, the brackets. So now I'm asking what's the covariance of a linear combination of such variables, and then the upshot is that all I have to do is to apply the definition and saying, okay, that's just whatever I had times an A on the left and an A transpose on the right. But remember that A is a constant, a set of constants, a matrix full of constants, diagonal or not. And constants, you know, they don't have any business with expectation. They're just constants. So you have A A transpose times the averaging brackets on what I already had. And that is then, I use my C again. So for a linear combination Z of random variables collected in a vector X, the covariance of that vector of variables is just the quadratic transformation, as it should be, of the covariance of the X's that you had. You want to call this X, you could call it X. And so now I want you to see that, of course, that then does simplify again to this thing here. And it specializes again to that thing here, and to that thing here. But so this is just a transformed variance of a transformed set. And we will need this all the time because very much of what we'll be doing is about linear transformations. The whole second chapter is about transforming things linearly, transforming data linearly to turn them into a model. And then if you start by having a covariance for your data vector, then you know what the covariance of your model vector is, and so on. That's one reason, so that's going to come back multiple times. But another reason is the thing that I said I wish I'd learned so much earlier. And I'm just going to briefly do it here because, this is where I think about it, and then it's going to come up later. So now let me make a vector of random variables. And let me jump the gun. I haven't even talked about the normal distribution, but here it is. It's distributed as normally with zero means. And variances 1 and covariances is 0. Yet more notation. So every entry, every variable is normally distributed, which we'll talk about later, with a little 0 as a mean and a little 1 as a variance.
That 1 with the 2 lines under it, that's representing a matrix?
Yes, it is. And so in particular, this one with the underlines, or maybe I should have written a big I, and I probably will at some point. I then mean the diagonal matrix of 1s and 0s on the off diagonal. So the notion here is independent, identically distributed, independent, 0 correlation, 0 covariance. Identically, there's only one distribution.
And those are the standard deviations for the
so here's another point of notation which is going to confuse you. I will probably always write the second entry of the distribution here as the variance. Now you're in luck with variance and standard deviation when they're 1, but I think my notation is going to be the first entry is the expectation, the second entry is the variance. It will get confusing because, for one thing, I think in MATLAB it's the other way around. It actually uses standard deviation, or maybe not, or I forget. That's how confusing it is. You often will think about variance as little sigma squared, and I probably will use that at some point. The most statistical literature just calls it big, fat, bold-faced sigma. And then where's the square, but I really use a variance. So right here and right now, I want to use the second entry to be the variance. In other words, the covariance, actually, I should say that's the covariance, right? It's the variance covariance matrix. It's that same thing as above. It's the thing that characterizes the variances of the variables on the diagonal and their covariances on the off diagonal. And when I write an identity matrix, other notation, maybe that's going to be like a big I, then I mean that identity matrix, the ones that are diagonal, which are the variance, and their independence, and so therefore there has no covariance on the off diagonal. So this is my example. And I'm going to continue on the next page because it's important. So here's my example. So now let me pick a certain covariance matrix that I like. So all I'm saying is there is a covariance matrix, and I'm going to call them it big sigma, 2 underlines to show that it's got all the interaction terms. And yes, it's a variance, even though it doesn't have the square on it. And that's not a sum, that's a sigma. And if I do an operation on it, which you may or may not learn or have already learned in linear algebra, and you can talk about when that's possible and how to do it and whatnot, but it doesn't matter. I'm just going to say that I can decompose this sigma into a product of some matrix L and another matrix L, and if I multiply their transpose, I'm back to sigma. It's another way of saying sigma is a squared operator, and L is like the square root. But in practice, this is a special kind of matrix. This thing is a special kind of decomposition, which you'll learn about or recognize as something called Cholesky, no doubt after a person. And I'm just saying, look, it's possible. Yes, this sigma is a variance covariance matrix, so it's quadratic and so on. It also has to satisfy certain conditions, right? The variance can't be negative and so on. And so positive definite is another term that you'll hear about. Positive eigenvalues, all that sort of stuff that comes with linear algebra. Here, just imagine it, got the variances on diagonal and the covariance that I like on the off diagonal. And I'm doing this decomposition for one reason only, is that if I begin with these z variables, whose variance I specify to be, standard normal, I should write covariance. Again, variance, covariance, the terminology drops the co or adds it on, doubles it up sometimes. But so I want to make this, I want to look, I'll write covariance because I've been doing that. So this is what I have. I specified the identity or the one matrix as the covariance of Z. Now I'm making a linear combination just like before. And now I'm asking, what is the covariance matrix of L dot Z? I'm going to walk you through it in a second, and then my letters keep changing, right? So previously I had an X, and I did A times X, and that was a Z. Now I have a Z because that's a standard notation for standard normal variables. And I have an L as my A matrix because L is a standard notation for a lower triangular Cholesky decomposition. And my sigma is my desired variance. So nevertheless, I carry on and I use my formula here for the covariance of the linear combination of random variables. L, the thing that I had, L transpose. And so what I come out with is as L dot L transpose dot times nothing, rather the identity, which means I have made a variance matrix sigma. So before you say none of this makes any sense, I want to tell you why I do this right now, okay? remember those point clouds and those smiley faces and all these other things? Well, somebody made that. And it is a good question to ask. You always will need to be randomly generating data because that's how you test hypotheses and understand probability and so on. So how do I generate 37 sets of random variables with specified variances and specified covariances between them? The answer to that question is, oh, that's easy. Just tell me what variance matrix you want between these 37 variables, apply a Cholesky decomposition to it, which is a one-liner in MATLAB, generate 37 sets of random standard normally distributed variables, form their linear combination, and you are done because their variance is the variance of the variables that you wanted. So this is a method to generate pairwise linearly correlated variables with a specified variance covariance matrix between them. I'll give you the code for it, but how to do it? Just generate a vector z of standard normals and multiply them by the Cholesky decomposition of sigma, namely L. In other words, knowing that sigma is L transpose. So that's how you simulate data. And I don't know about you, but I find this by far the most useful thing I've ever learned. Because you always want to prototype things. You always want to test things. You always want to generate random variables. And you always want to explore the effect of correlation. So I'm writing the follow, right? So I went through vectors of random variables, multiplying them by matrices that are linear combinations. Now I'm saying, if you want to generate pairwise correlated variables with a certain specified sigma between them, just generate z standard normals, multiply them by the Cholesky decomposition of sigma, which is L, which by definition sigma is L times L transpose. So later on, not so far in the future, we'll be doing linear regression, picking lines to two variables. We'll be looking at error propagation, because they're linear models. We'll be applying everything from here as a matter of course. And any simulations we will want to be doing, we'll be using this fact that if you want a multidimensional set of variables with specified correlations between them, that you can start from the standard normals and transform them into something else. So if I back that up, so now normally I would have my board full and then go, let's now look at our boards, right? Combining by addition and multiplication, in other words, linear combinations of variables. And there's just two, a times one plus b times the other with some constant. We know how the expectations vary. It just carries through. We have the intuitive notion that the variance, which is a measure of spread, which is a measure of the quadratic measure of things. Quadratic is the average squared distance of something to its own expectation. There's going to be squares coming out. So simple linear combination, ax plus by. I mean, I could jump to the conclusion and say that's a squared, the variance of x, and b squared plus the variance of y plus 2ab. But it is rather an example of a much more general rule, which applies to a weighted combination of variables, where it turns a vector of variables xi element into a single scalar z variable. And then that is how you combine and get the single variance of that thing. Then I made that one more step generally and said, now, let x remain to be a vector, but let's replace this with a matrix, and then we get a vector of z's out. And that was this example, was it? Where my ith element of whatever vector I create is some, matrix row times my matrix column times my vector. Examples: a diagonal matrix. which turns a vector into a vector, and all I've done is like 3 times the first and 2 times the second and so on. The other case that we had before of the weighted linear combination resulting into a scalar, no underline, is just the vector dot vector. Then I had a dot product like this. Then I do want the outer product like that, where I now visualize it in row and column vectors. I make a definition of that, which is a standard notation in many fields, where XX transpose is a new matrix Y doubly underlined whose ijth element are the xi, xj. No dot. It's not a dot product. Then I did that because I wanted you to start thinking about covariance matrices as averaged outer product of vectors. If I want to characterize the individual variances and all the interactions between any variable that I may come up with, it is natural to combine them in this way, because if I read these elements off, then I have the xi, xj variable, and that entry here in its expectation, provided these are all individually demean, that's the covariance between those two. The diagonal ones are the variances. So if I went back to this vector with this matrix vector multiplication, which turns into a whole new vector of weirdly weighted summed variables, then I know that the transformation of their variances is just left and right multiplied by that A matrix that I choose to cook up. Example, A is a special matrix if A is the square root, or Cholesky decomposition, of some acceptable variance matrix that you may like. Then if you begin with a variable set that has an identity matrix as a variance covariance matrix, so an independently uncorrelated, identically distributed, take the normal example, and then you multiply them by that square root of some desired sigma, then you have just made yourself a new variable. Actually, I might call that y. And so if you begin with a z that is just uncorrelated standard normals identically independently distributed, then you make a new normal distribution where, sorry, that's not a matrix, that's rather a vector, so a single underline. And so when y is L matrix dot z vector variables, then all I know now is that the variance covariance matrix, the cov in my other notation of this y is the thing I wanted. And while I didn't make that picture on the Wikipedia with the various correlation, that is indubitably how they made it, by transformation of some IID unit variance matrices and then making any sort of correlation between them.
Can you do this decomposition with non-normally distributed data?
Yes, I didn't need this to be normally distributed. We are going to talk about how when you combine normally distributed variables, you end up with normally distributed variables and so on. Really, the minimal element that I had here is that IID, independent identically distributed variables with a unit variance between them, so identity matrix, when linearly transformed with something that squares to an acceptable variance matrix, will have that variance matrix that you want as their variance matrix. I only really talked about the transformation of a variable and what happens to the variance. I didn't actually talk about the distribution or even need this to be normally distributed. what we do need is that this sigma needs to be able to be transformed in this way. And if you're going to stick in -1 and imaginary numbers, it's just not going to work, right? So for something to be an acceptable variance matrix, it has to be symmetric and positive definite and all the things that you associate with it. But you cook one up, and so I have multiple codes, but maybe I'll give you the one example if you want to see it. So, fake relation, okay? That's my mini code to do this. It's on my one of my GitHub pages. And maybe it's not perfect, but it's what it is. So, all right. Cook up a desired population covariance matrix. I call it CXX, CXY is for pairs now. It's not multi-dimensional. And I already know it's going to have to be a proper matrix. So that only has 3 elements, even though there's 4 I need to specify. So here, my default is make it unit variance and then have a half covariance in between. I rearrange to make sure it's a proper matrix. So C121, C122, C122, C123. Then you define your distribution. But you want to change it, you change it. This here, you don't want to change because that's the unit variance that you begin with. Then you just generate a vector, which means 2 sets, because I got 2 entries, of random values with those. So they are uncorrelated because you're doing them in 2 different lines of the code, and they have unit variance and 0 mean. Then you're asking for the Koleski transformation of the thing you want. Then you make the pair. And then you extract it.